Section 3.10 is called torque, inertia, and change of speed. And this section brings to us a concept that it's a little subtle, but I want you to think about it and work through it and remember that this is important in understanding how electrical machines operate. But he makes the statement in the text where he says there's only one way to increase the speed of a motor, and that is to apply a torque for a set amount of time. Now, what we're going to do is we're going to work through some problems specific to that idea, and we're going to quantify this. And I think you'll find it sort of interesting and eye-opening, and you may not have thought about electrical motors working this way before. So here's our basic equation that allows us to quantify this idea. Again, that idea is the only way to change the speed of a revolving body, and we're talking about a motor or a generator, is to subject it to a torque for a given period of time. The rate of change of speed depends upon a few things. One of them is the inertia. So the greater the inertia, the less the change in speed, and also the torque. Now, I've written this equation 314 up here for you. This is on page 57. And here again, here's this constant again. And, I just briefly, we don't have to derive it, but, I think some of you are probably like, well, where does that come from? Really, it's a constant because we're working in SI units. And so we would normally in SI units, we would be dealing with radians per second. The constant 9.55 allows us to work problems that are given to us in revolutions per minute. And we will see when working with motors and when we get to the lab and we're measuring the the rotational speed of this, what we want to do is to work in RPMs. So 9.55 allows us to do that. So that's that. This T is the torque in Newton meters. And this delta T is the amount of time or interval of time which the torque is applied. The J, again, is our moment of inertia that we've talked about earlier. So there's our problem. And he goes on to explain, he says, if the torque is applied in the direction of rotation, the speed increases. If the torque applied is in the opposite direction, the speed falls. Eventually, the speed would become zero and the revolving body or motor would reverse directions. The delta N, therefore, represents either an increase, positive, or decrease, negative value. So the specific problem he has for us is on page 57, example 311. We've got a flywheel, which we should know what that is now, and it's turning at 60 RPMs. And we need to increase that speed of rotation from 60 to 600. And we're able to do that by applying a torque of 20 Newton meters. Okay, so think about that. We have a torque that we can apply to this revolving body. How long we apply that torque to this revolving body will determine, the change in speed. The longer we apply it, the faster it will turn. So how long would we have to apply this to reach 600 RPMs? Now, I want you to think about that in practical terms and think about a motor and an application, and you have some process that the motor needs to increase for this process to take place, and you have to say program, PLC or whatever is involved with this so that you can increase the rotational speed and timers and all this would be a part of this calculation. So, this is a real thing. It's a relevant, real thing. It's not just some exercise. So to work this problem, the first thing he tells us, or first thing we have to determine is what is delta N So the change in speed, it's going from 60 to 600. So that change of speed is going to be equal to 540 RPMs. And that's going to go into here, okay? So in this particular problem, we're given what that delta N is. So what we're trying to do for this problem is determine what delta T is. All right, so it's a little bit of a different calculation, and we'll get there by doing a little algebra and solving equation 314 for delta T. So here's our equation solved for delta T, and you know, just rearranged here, right? So what we're looking at is how long do I have to apply this force of 20 newtons? Everything plugged in here. Delta N is 540. That's the change in speed. The J number is given to us as 10.6 kilogram kilogram meters squared. And how do we know that? Well, because it relates to that earlier figure, figure 311, and we got the moment of inertia, you know, going through that problem and looking that up and you know, seeing which one matches to it. Okay, so here's our constant and here's the torque, right? So here's this solved for delta T. And in this particular case, we multiply this out, we end up with 29.97 seconds, or approximately 30 seconds of an application of 20 newtons of torque will cause this revolving body. We like to think about motors or generators, you know, for our purposes, will cause it to go from 60 RPMs to 600.